Test 1, 2. Hey, hey, there we go. So did everyone enjoy the coffee talk? Remember, properly caffeinated, things of that nature? Well, that's good. So just a couple of announcements. We've got the hardware hacking area open next door. We've got the Legos over there. I'm going to fire up the CO2 laser in just a little bit. The vinyl cutter's going. I believe that Rios is going to come down and actually start playing around with some of the badge stuff. If I understood him correctly, he's bringing down everything we need to do skillet reflow and hot air reflow, which is how the SkyDogCon badges the electronic badges were produced. So we'll be in there playing with that. And if you've never done surface mount stuff, it's a lot of fun. So hopefully we have some good times with that. So next up, we're going to have Sonny Mounicou. He's going to come up and talk about equipping a hackerspace. We know Sonny is Osiris online. He hangs out in the Hacker Consortium channel a lot. And typically we'll spout off something about, oh, I was cutting something on the laser the other day, and we'll post a picture, and then Sonny will pop in and go, yeah, done that. By the way, you might want to change this setting this way. So he's been really helpful for us in diagnosing issues with running the laser and some of the things that have happened to us. I think he took receipt of your laser a year before I got mine, and I think it was sitting in his possession for 20 minutes before you fired it up and started cutting stuff with it. So he's really quick on getting all this stuff set up and running. And if you haven't seen, they had the Pruses out here in the open area, in the expo area yesterday. I believe they're now in the hardware hacking area. So if you get a chance a little bit later, they should be running. You can check those out. And if you've got any questions, I'm sure they'd be glad to answer anything you've got. So without further ado, Sonny.
I want to start off by thanking SkyDog and Some Ninja for asking me to come out here and do it. I know it's kind of a different tangent to a lot of the other ones that are going on, a lot of the other presentations, but I think it'll be fun and it'll give you a good perspective. Also, I'm not sure whether I'm helpful or annoying, or maybe a little bit of both. Can you hear me? All right. Test. Test.
There you go. Now it's on.
All right. All right. Great. So the most important part is obviously to turn it on, which I guess I'm too caffeinated to remember. So anyway, what I was saying is I'm not sure if I'm helpful or annoying in the channel, but I try my best to help others out as they go through a similar journey that I have been through. So I also wanted to thank SkyDog and Some Ninja for inviting me out here, because it's a fun tangent. So without further ado, I'll get started. My background, I actually have no machining background whatsoever. I'm actually in software development. I'm a director of business intelligence for Medco Health Solutions. So I do something completely and totally different than what a lot of folks do. But I do a lot of software development, and I do lead those teams, and I'm pretty well versed in it. But a lot of this stuff I've learned myself. You know, I'll buy the pieces, I'll learn how to use them. It's all about self-journey. I don't have any formal training in what I'm about to talk about today. So some of it may be right, some of it may be wrong, but it'll be my anecdotal information about it. And that's really why I'm here. You know, a lot of us will decide that we need to do something. Maybe it's 3D printing because we've seen it online. Maybe it's getting a laser cutter because we see what it can do. Maybe it's buying a mill or a lathe because we have a vision of something that we want to create. And a lot of us don't have the opportunity to get that sort of training. A lot of us don't, we can't go to the local community college because of time commitments or money commitments or family commitments. But nonetheless, this is my journey. So I'm going to go over a lot of different technologies that I use, some of the different projects that I've created, some of the different things that you can do with the machines, and some of the different considerations that you may have as you build it. And throughout this, you'll see examples of things that I've created. Just about everything in here, I think actually everything in here, I've actually created with my tools, with my with my equipment, and I'll speak to it as I go through. So this particular one is the Mid-South Makers badge. I am the interim president of the Mid-South Makers. It's a hackerspace in Memphis. We've got a number of folks out with me. And this is laser cut out of blue fluorescent. And you can see it comes out pretty nice. It's in the same frame as most everything I do right on the laptop. But it's pretty neat. So the agenda. I'm going to start talking about 3D printers. A lot of folks have seen them or heard about them. A lot of folks know them as MakerBots. But really, I want to give everybody a little bit better background about what it can do and what it can't do. A lot of people look at it like it's black magic. You know, it creates parts out of nowhere. And to some extent it is, but there's a lot to it. And I want to give folks a little bit of a background as they think about jumping into that journey. I'm going to talk about mills a little bit. I'm not going to go into great detail with them, but I'll give a good overview of what you might look for, what you can do with it, why you might want one. Same with lathes. Just a little bit about my journey into that. Laser cutters, I'm going to go through that. The software stack is often overlooked, but to be quite honest, having all these machines is quite useless if you can't use them to create something. And that, to me, is the missing link, and it can be the most daunting task of anything. And then I'm going to briefly go into electronics and just talk about some of the electronic pieces that I use to create some of my creations. So first, I want to start with 3D printers. So I'll explain what you're seeing right here a little bit. This is a body for a quadcopter that I'm designing and building. You can see that it's being printed right on glass. It's using a material called PLA, polylactic acid. And it actually is extruding, and it's going in a Cartesian form, basically X, Y, and then it'll roll up Z to the next layer as it goes through. And you'll see a little video of it next, but that's effectively what a 3D printer is. So with that, so now you can actually see the video of it going at the bottom. You know, I just mentioned a second ago, it is a Cartesian bot. So if you were to think about it like a 2D printer with multiple layers, that's probably the best way to think about it. You know, every layer is independent in and of itself, and so it will build. So it'll do a bottom layer, and then it'll do a higher layer, and it'll continue to roll up. You can see it going across. One of the neat features you can see in the video is that of acceleration. The RepRack project and just 3D printing in general is maturing extremely fast. And so when I first started with it, there was no concept of acceleration, meaning that it used a constant speed to move from one end to the other. The challenge with a constant speed is that you can't really take advantage of a very fast movement, because what happens is if I were to set it at, say, 250 millimeters per second, what it would do is it would actually rip itself apart, because the torque, when it moved, would actually take it away. But what happens here is by acceleration, I can slowly ramp up that speed, and that allows me to get a very good run going across. So you'll see it's almost like a dance, if you will, as it moves across the top. And it helps to have a big platform, most certainly. Now on here you can see a couple of things that I did, and I'll just go over that briefly. You can see at the bottom I've created some support material. 3D printers can't really do overhangs today because it builds successive layers. And so what winds up happening, we call an overhang something that's less than 45 degrees. So if you were to think about a 45-degree angle, if I were to have anything that went this way at a lower angle, what would wind up happening is it wouldn't have a layer under it to support it, and so the filament droops down. So what you can do one of two things. You can design everything such that it's greater than 45, or you can build support structures that help, and they break away very quickly. So in this one, and it's kind of hard to see from back there, but I'm sure you can see it online a little bit better, there are actually 4 little tabs at the bottom. I created those 4 tabs in the design software as just hollow cylinders that supported an overhang. The reason I did this was because I wanted the overhang to work properly so the electronics could stick out, and that basically allowed me to build it that way. So there are workarounds for everything, but that's the start. So what can you really create? That right there on the side is a cube gear, a screwless cube gear. I'll build one outside today as we're sitting in the expo area. But effectively, it's motion. It does move. It's got PLA pins that hold it together, and it's a set of gears that turn. It's neat because it's something in motion. You can actually move it. It's functional. It requires a little bit of parts, but it gives you an idea of the creativity that you can express with it. So when I talk about three-dimensional objects, Really, the only limitation that you have, or the biggest limitation that you have, is the overhangs. Other than that, anything that you can imagine, you can effectively create. Now, it does build it into layers, so you do get a somewhat layered appearance with three-dimensional pieces. But it's not a, most of us can look by that as we're building things with 3D printers. The other thing is to talk about materials. So there are a couple materials that have come and gone in the scene. A lot of folks use ABS. That's standard ABS plastic, and it works okay. It requires hot temperatures, so you typically have to extrude at 220 degrees, and you have to run a heated bed, which I'll talk about in a little bit, at about 120, in order to keep the material from warping. It has a horrible scent, which is pretty pervasive, and it is very prone to warping, so you have to be careful. The ABS itself is very flexible is not exactly the right term, but it's soft enough to where it can take a little bit of bend and it won't break, which is very useful in certain objects. What I typically use, and what a lot of folks use in the RepRap community, is called PLA, which is polylactic acid. Polylactic acid is it actually works a little bit better. It's more brittle, but it's harder. So I could probably stand on a piece of PLA without breaking it, whereas I couldn't with ABS. It won't give, but it will shatter. So if I were to make a kid's toy, which I've made many of, I would probably make it out of ABS instead of PLA. Because if you make it out of PLA and you throw it up in the air, when it lands, it's going to shatter into a few pieces. The other example I typically give is if I were to make a projectile, if I were to talk about weapons, if I were to make a projectile, I would probably make it out of PLA. If I were to make I would probably make it out of ABS. If I were to make a knife, I would probably make it out of PLA because it would be harder. So how does it work? Really, it's thermoplastic extrusion. So you take filament, it runs through the top, it's pushed down via a motor through a hot end. The hot end typically uses nichrome, and nichrome is used in hot wire cutters. It's used as heating elements in a number of different heat technologies. And basically, that's typically wrapped around a brass rod, if you will. And so the filament's pushed through. It melts it, and as it comes out, you control the flow as it goes through. Now, you can see in the picture on the right, this is my MakerBot with a lot of upgrades to it. I was actually building a space shuttle for my son, and it's a good example of what you can build. Things are moving toward, for larger objects, paste extrusion tends to be something that things are moving toward. The economies of using PLA or ABS plastic just aren't there if I start talking about large objects. As I get above the body, the print volume of a Prusa, it gets extremely expensive to print objects. And you typically don't need the level of detail that you're looking for that you can achieve with plastic. So with paste, such as I think plaster is used. I've seen very large ones using concrete. You can find ones on YouTube. They typically use compressed air and/or some sort of pressure to get the information or get the fluid out. And sometimes they use linear solenoids to push it. It just depends. But paste extrusion is where some things are moving to. If you go online and you look at the Frostruder, or you look at Fab at Home or some of those other technologies, you can, or some of those other vendors, you can actually see them doing chocolate. You can see them doing cookie dough. You can see them doing icing. That sort of gives you a perspective of what you can do. In fact, I've thought it would be quite creative to use a frost extruder to actually, put out cookie dough and then use the heated build platform to bake the cookie dough. All right, so a couple of different options as you start looking at it that a lot of people typically ask about. The first one is the type of motor that articulates the extruder. And originally it used to use DC motors, which are just RPM driven. And the challenge with DC motors are that you've got very little control over the distance that it moves. So you basically send it a voltage. You think that it moves a certain amount. You hope based on timing and voltage that it did. But if it didn't, it's challenge. It didn't work properly, and you have no way of knowing it. And also, reversal tends to be very hard on DC motors. So there are times where when I'm printing, I actually want to reverse the filament. An example of that might be if I have a gap between two areas. I actually want to reverse it, move the head over to the other one, and push it back down. The reason for that is because you've got back pressure inside the nozzle. And so if you don't pull the filament back up and relieve that pressure, you're going to get a drip, if you will, or strings that run across the print. So what you do is it actually pulls up very quickly, and then it moves the head. With a DC motor, that's very difficult on the motor. Often reversing those that frequently will cause issues of it failing. And so things over the last, I would say, 6 months, well, no, actually more than that, probably the last 11 months, things started moving towards stepper extruders. The good thing about a stepper extruder is that you know I can calibrate it and I can tell it how many steps to move. And provided that there wasn't anything that stood in the way of it going, I've got a very precise control over the exact amount of filament that I push down. And it allows me to have very, very good control. It's responsible for probably, I would say, a quadruple improvement in the print quality of the open source printers that we've had. It's really a phenomenal difference. The next one is a heated bed. So with a heated bed, it's important for two reasons. For ABS, you have to have a heated bed or you're going to warp. And the reason you get warpage is because as you move up successive layers, the bottom layer has the opportunity to cool. And so if I look at an object that's, say, 4x4 or larger, what happens is the bottom starts to arc up like this. Now, it doesn't affect the top of the print, but you wind up with a print that has a rounded bottom, which isn't really usable. And so the heated bed basically just keeps it on a warm temperature, not as hot as the extruder, but hot enough to just make sure that it doesn't warp. And typically, you run those at about 70 Celsius for PLA and about 120 Celsius for ABS. Now, with PLA, I use it for a bit of a different purpose. Technically, PLA doesn't warp, so you don't need to use a heated bed. But the advantage, I am able to use glass on top as the platform and the heated bed to make sure that it sticks. And it winds up being a very convenient structure. A lot of folks will print without PLA, without a heated bed, directly onto blue masking tape, onto aluminum, which works. It does okay, but you have to remove the tape all the time. You have to change it between prints. It's a real pain in the butt, and sometimes you have to pry the blue tape off of the bottom of your print, which can take longer than the print itself. With the heated bed, I can actually print PLA on a piece of glass, and when the temperature gets back to 40 degrees Celsius, it just pops off. The bottom is glass. It looks just like glass. It's beautiful. And you guys can see it outside. All of the Prussias that we've assembled from Mid-South makers are using glass because it's just extremely convenient and it's cheap. No tape, no mess. I highly recommend it if you're going with a machine. Now, the caveat to it is it does require a lot more amperage. You're probably talking about 10 amps at 12 volts in order to power it. So you're going to have a beefier power supply to move it. But the heated bed is about $50, and the glass, I think, is $250 from Lowe's or Home Depot. And I'm using, you can't see it in the picture, but you can see it out there. I actually use binder clips to hold it down to the PCB. I mean, it's pretty nominal. The other item on here, you've got linear motion. When this particular, the model that we use, Prusia, when it first started, there was a vision that you could get all the electronics, or I'm sorry, all the hardware from a local hardware store and then actually build it. So you could do everything locally provided that you had the printed parts. And so originally it used what's called PLA bushings. So little bushings that slide on the rod, and they worked very well for some time. But they erode. I mean, it is plastic. It does eat away. Over a period of time, it starts to shake. They're not quite as precise because they're not machined out of metal. There can be some challenges with it. So to jumpstart the process, they worked great. And I'm happy that I had them. But I've moved my machines, and the other folks from Mid-South Makers are moving their machines over to linear motion as well. And by that, I mean that we use Element UUs, which ride on precision rods typically. And it allows us to get a much better quality and a much smoother motion. And what happens is I can actually turn the amperage down on my steppers because it's just that much smoother. I can run my machines faster. With mine that sits out there, I've run it at up to 280 millimeters per second. And for example, with my MakerBot, the most I could achieve was 40 to 50. So you're talking about 5 to 6 times the speed of what I was able to do before. And compared to a Prusia with PLA, that caps out somewhere around 60 or 70 is kind of pushing it. But with linear motion, you can push it way up and don't have a problem. I highly recommend it. If it is an expensive option, but it makes the quality and the convenience a lot better. You can move it much better. So electronics is the next one. There's a big variance, and there's a lot of, let's see, there's a discrepancy in the community about how things should go with electronics. So some of that confusion is reflected by the fact that there are so many different choices for the electronics that you can go with if you go to reprap.org. You can see there are simple ones like the Sangalulu and the Teensy SOU. Those are ones that typically can be etched at home. Gen 7 is another example of that. You can etch them at home. You can buy all the parts. You can put them on. It's a cheaper way to go. It works fairly well, but it is more of a low end. You don't have nearly the capabilities on the AT Mega that you put on those that you have with some of the other options. So it's a good starter, but I typically don't use it, nor do most of the folks from Mid-South Makers. We have one gentleman who did. He etched his own board. He set it up because he wanted to do it on at a very low price. And he's been successful with it. So it is an option. I use what's called ramps, which is it's a rider board that sits on top of an Arduino Mega. So that ramps board has the spots for the stepper drivers. It has the MOSFETs to control the heaters. It has all the different pieces that you need really to make it work. And it's very convenient to use. It's designed by a guy named Johnny from a company called Ultimachine in Knoxville. And he's a real good guy. But it works extremely well. It's a more expensive option. But it also gives you greater capabilities down the road. It has an extra spot for, the newer models have extra spots for a fifth stepper if you want to look at dual extruders and things like that. So it's moving in the right way. It is by far the most popular option to use if you just want it to work and you don't want to have to futz with it. It just depends on how you want to go. And lastly, a lot of folks don't understand, what is this little MakerBot versus RepRap versus other different commercial vendors. There are a lot of vendors that compete in the low-end range of the hobby class of these printers. And you can see, MakerBot is a good example of that. They used to sell a $750 cupcake, and I have one of those guys. Now they sell what's called the Thing-O-Matic, and they've got a lot of folks that use them, and a lot of folks like them. They are so popular that things have become synonymous. People just call them MakerBots. RepRap is the open source version of that. RepRap started the process with a machine called the Darwin over in the UK, and it's really the first version of the RepRap that could do it. It was very cumbersome, difficult to use, but it slowly evolved to where we are with the Mendels. MakerBot has leveraged that, and they've also added their own pieces to it, and they do donate things back to the community, and so I don't want to make it sound like it's an HP or something like that. They do take the designs, they do release them back. They are fairly open, but not as open as RepRap, where people tend to print their upgrades. They tend to roll through it. It's the equivalent of, actually, I don't know an equivalent in the commercial world while I'm talking, but RepRap is the way that I would recommend you going if you decide to go with a 3D printer. It's the community supports you. There's a great evolution there. You're on the bleeding edge. It's the right place to be. And then lastly, I put in there Up. Up is a company. It's from a company called I think it's PP3DP from China actually. They have a very good small printer that works. It's fairly expensive. I want to say it's right around $2,000. There are a couple of other companies like Bit for Bytes. There's Ultimaker that you can see that runs theirs very quick. Some are open, some aren't. Up's not. The Ultimaker is, but the electronics are impossible to do by hand. So it really depends on which way you want to go. But if you're looking to get in cheap, RepRap is the way to go. And I included a picture at the bottom. I was at Maker Faire New York City a little bit ago. And at the bottom, you've got Prusa, who actually designed the Prusa that you see in the picture. And you have Bree, who is one of the founders of MakerBot. So it's kind of funny to see the two talking side by side. There's a bit of animosity there, and it's a bit like a Star Wars reference to Darth Vader and Luke. All right, so just some considerations. Additive CNC allows complex shapes to be created, which are impossible on subtractive CNC devices. I am creating a lot of the devices for my quad that I've created I could have never done with regular CNC machines. I can't mill the parts away that quickly. It's just impossible to do. Additive allows me to build things in successive layers and build inner structures that I just can't do with a subtractive CNC. There's a real rapid development from design to implementation. I can go from one spot. I can take something from my mind and implement it very quickly in a very short period of time, and it works very, very well. And then the learning curve. It is a strong learning curve. Typically, from the time that people have their machines to when they're productive takes weeks or months. Your first couple of weeks are going to be spent printing cubes and figuring out how to make cubes look good. And then you're going to go beyond that, and you're going to start creating more interesting things. You'll download things from Thingiverse. You'll get more comfortable with creative designs. And then you get to a point where you're designing improvements for your machine and doing things like that and committing back to the community. But that process for a lot of folks takes a good bit of time. For me, I'm finally where I'm doing that, designing my own pieces, or at least I have been since probably about June. And it took me a couple months before I was really comfortable turning things around. And so I need to talk quicker because I spent a whole lot of time talking about 3D printers, and I am quickly going to run out of time. So mills. This is an example of my mill at home. I'm milling the plate for my quadcopter, and you can see it's actually cutting out the piece. The video ended, but you can see it's cutting out the groove in the middle. You can actually see the result of that groove right there at the top. You've got the four arms, and they sit within those grooves. It's an example of one thing that you can do with a mill, just an idea. So two-dimensional objects are one of the primary things you create. And when I talk about that, it's really, think of it like a plate where I can choose a depth for each operation, but the depth for the operation is consistent. So if I wanted to cut a groove, from one end of the groove to the other is typically a consistent depth. I could cut all the way through and do an outline, or I could cut pieces out of it, but it's always consistent. As I move to three-dimensional objects, which I've actually done none of on my mill so far, you can create contours. So if I wanted to create a Mickey Mouse, or I wanted to create a model, a design, a groove, a slope, I would do a three-dimensional object typically. And it's a little bit more complicated. You use ball end mills and a few other things, but it can be done. And lastly, the materials. If you think about getting a mill, you really need to focus on what materials you want to use and what materials you want to cut. When I started the process, I really had no idea. I bought a V90 from Probotics, which got rave reviews, and I started there. But it's a gantry style, which I'll speak about in a minute. It can do aluminum, but it struggles with it because of the rigidity. It's fast, but there are a lot of compromises where it just can't hog metal, and the precision isn't as good as you would like to do PCBs. So there are a lot of trade-offs as you go with it. If you're mainly worried about doing aluminum, or I should say, if you're mainly worried about wood and plastic, I wouldn't hesitate to recommend that. But if you're looking at doing other things like some of the metal, it gets a little more complex. So on the picture up here, you can see the outline for the quad that I did. You can also see some Acme nuts that I did. Those I actually created on my mill, so I carved the thread within them. I did that because they were very expensive, and that worked pretty well. And at the bottom left, you can see a PCB. I actually milled the circuit board on my mill. Those are all examples of things that you can do, and I have done. So I probably won't spend too much time here because I'm running short of time. How does it work? Basically, the way you think about a vertical mill anyway is like a drill press. A drill press is typically used to handling vertical loads, but with a mill, it's used to handling horizontal loads. So I can articulate the table and move the table into the cutter and actually cut sideways. That's really one of the ways to think about it. You do have manual versus CNC options. So manual means I'm rolling dials in order to make it move. If I'm looking at doing very simple things, that works extremely well. I can cut a groove that's just 90 degrees or horizontal very easily. I can drill a hole with an end mill very simply. But it's limiting if you want to do complex things, and CNC really opens it up. It's a little bit more expensive, but now the machine is controlling it. So if I need to cut a 45-degree line and I don't want to rotate the workpiece, I'm actually able, I could not spin the two dials at an equidistant fashion and make it a perfect 45. But with a CNC, I don't even have to think about it. I punch it in and it does it for me. It's a lot easier and it's faster. The other thing to think about with a manual versus CNC is that I don't necessarily need as many bits, and let me explain what I mean by that. With a manual mill, I have to be very careful when I drill a hole that it's or let's say if I drill, not a chamfer, but if I actually put a taper within a hole so that I can put a screw inside it, typically I would use a reamer to do that. So the reamer would actually carve a spot for the head to go. But that's an extra bit that I have to buy or that I have to make that can be expensive. But if I've got a CNC, I'm just going to use a regular end mill, and you've already got a gamut of end mills. So that end mill can actually carve the spot for the socket to go or for the head to go very easily. It makes it a lot cheaper for me in the long run because I don't need such exotic tooling. I can also use end mills instead of drill bits when I want to use precise diameters. And then the types, you've got vertical, which is like the tag at the top, where you've got an arm and the head sits on that and the work plate moves. And then you've got a gantry style. You can see a V90 on the right there, so the actual the work stays still, and then the head basically moves over it to do what it needs to do. At the bottom left, you can see a ShopBot, which is made for doing 4x8 sheets of plywood, and it's actually cutting a train for my son. So options, there are lots of bits. I talked a little bit about end mills. I talked a little bit about ball end mills and chamfer bits and some of that. I won't go into it with great detail. A fourth or a fifth axis is nice because that opens up your options on what you can do. When I think about if I wanted to do a gun stock, for example, having a fourth axis, like you see it right there where it's mounted vertically, now I have the ability to actually carve the gun and carve the gun stock, and as I rotate it, I can actually change it. People will do that with pool cues, gun stocks. Gun stocks are very popular. Also, with a fourth axis, it becomes very easy to do jewelry. So a lot of people will actually mount it on, and they'll carve a ring, and you rotate that rotary table, and you can carve the design in the jewelry. So a lot of people will use these tags to do that jewelry in wax, and then send that off to be created in metal. And fifth axis is a little different. I wanted to include a video here, but we don't have time. Fifth axis is where I can actually move it in almost any direction. I'm not really tethered by the way it's controlled, and it's kind of difficult to explain. But you can see examples on YouTube of them actually carving motorcycle helmets using a fifth axis because I can get to the sides. I can almost get under grooves. It's a phenomenal capability. And if you've got if you can get there, then it's pretty cool. I've actually got it to where I've almost got a fifth axis on my tag. Now it is limiting. I could never do a motorcycle helmet because I don't have the Z height, but I could do lots of creative stuff like little toys. Spindle speed sensors and control. This is critical for a number of reasons. You want to know if your mill is bogging down, and the spindle speed sensor lets you do that. You want to be able to control it. So I may want to run different speeds in different areas, and having the control means that I don't have to sit there and pull a pulley off and change the belt, move it to a different thing, then start it back up. All I've got to do is literally punch in the new RPM and let it go. For the lathe, it's even more critical. And table fixtures, the way that you mount these things down is absolutely critical. You spend 90% of the time associated with these mills trying to mount the work to the table. I'm going to repeat that because it's crazy. You spend 90% of the time mounting things down. It's very difficult to do. It's complicated. It's hard. Actually designing it, running it is easy. There are many times that I will spend 3 to 4 hours mounting something right just to spend about 5 minutes milling. It borders on absurd. But you have to do it, you have to realize it, and you have to know that you have to have the equipment to make it work. Because if you don't have the vices or the hold downs or the T-slots or the T-nuts that you need to do it, you just won't get there. I put a different page in here for PCBs because they're a little bit different. For PCBs, you want a very fast spindle speed. The one that you saw at the top right that went away, that spindle moves at 26,000 RPM. Commercial variants move at over 100,000 RPM. They're typically water-cooled. It allows you to do a very, very fine cut. You can do SMD traces depending on the bits that you use. But spindle speed is very critical. So you couldn't use a standard Bridgeport with a 2,000 RPM and hope to come out with good quality traces like these. It just won't work. Work holding, I use a vacuum chuck to hold my work down because it's the most convenient. You can, there are tons of different ways to do it. Some people will actually use super glue and super glue it down and then use acetone to pull it off of a plate of aluminum. That works okay. But I like to use a vacuum table because it's very quick. I don't have to deal with those chemicals. I push a button to turn it off and the piece comes up and it holds it down completely flat. And then for bits, I use precise bits for the things that I do. There are lots of eBay variants where you can get standard V-bits. They're not very expensive, and you really need special bits in order to do that. You'll see 45, 60, 90-degree bits. I typically use 60s and 45s because they're the most common. But if I wanted to do some really crazy TQFPs, I would probably use 90 bits. All right, on a lathe, you can barely see the video there, but I'm actually turning a radius. That's another example of why CNC is more powerful than using a standard manual lathe. Because here, typically if I have a manual lathe, I build a fixture that can actually rotate the bit in a basically semicircle to carve the round edge. But with this, I literally just tell it what I want the radius to be, and it articulates the motors appropriately. Something I could never do by hand without having specialized tools. And those pieces to do the radius would probably cost you, I don't know, 50 to 100 bucks. So by the time you add up all those specialized things, you get to where CNC would have just been cheaper and easier. So what can you do? You can carve cylindrical patterns and objects. I say this because it's you can do square objects if you want to. If you have a 4-jaw chuck, I could take a square and I could bore a hole in it. I can use an independent 4-jaw chuck, and I can actually do it off-center. So I could do lots of things in creative places. It doesn't have to just be in the center of it. Those are not the easiest to do. Typically what I do, I use a 3-jaw chuck, and I do a lot of round stuff. So at the top, you can see some couplers that I made for my Prusa. Those were made on the lathe before I CNC'd it. It was very manual. It was very easy to do. I made a set for Dan as well, and it works well. You can bore holes. When you use a drill bit isn't that accurate. There's a lot of wobble in it. It's not that clean. The way that it cuts, it's not as precise as you would think it would be. You can actually use what's called a boring bit and make a very, very clean circle within it that has great tolerances, and that's what you want to use for certain things like lead screws. And then lastly, you can thread objects. You saw that it did it on the mill. I've actually not threaded anything on my lathe yet, but you can create threads in objects, which are very nice, inner or exterior threads, and that's a very powerful feature. So how does it work? Basically, the material goes into the chuck. You spin that at a given RPM, and then you're going to put a blade onto that and actually cut it. So your work is moving very, very quickly. For work holding, you're using a chuck. So I'm using a 3 or a 4-jaw chuck or an independent chuck. There are bigger ones. If you've got Bridgeports, you could have 6-jaw chucks. But for the most part, I just use a 3 or a 4. And for work holding, it's very simple. They just go straight in the chuck. Now, if I were to do something different, and I'll talk about it under options, so I won't now. For bits, you've got choices of high-speed steel, carbide-tipped, or other exotic ones. I typically use high-speed steel because it's simple and easy, but I'm about to start experimenting with carbide bits because I can do more with them. And then manual versus CNC, we've already talked about that a little bit. The CNC gives you a lot more capabilities, but the manual works okay as well. And I'm burning through this pretty quick, so I think I'll get us back on track. So a couple of options that you should be aware of. There are items like arrests at the top. There's a follower rest and there's a steady rest. So there are times where I need to carve a piece that's long and it won't necessarily fit. So if I have, an inch worth of chuck that can actually hold the piece, I can't cut a 7-inch long item, because what will happen is as soon as I push, it will actually spring out of the way of the piece, and I could actually send the piece flying off. So there's something called a steady rest, and a steady rest actually sits further out from the chuck, and it has typically 3 pieces of bronze or brass that support for the cut so it doesn't spring, and it allows you to do things that are a little bit longer than you could if it was just mounted in the chuck. It's a way of giving extra support and making it safer. There's also something called the follower rest. So if I have when I'm moving the gantry and I'm cutting, let's say I have a very long cut, like a knitting needle, or a pool cue might be an example. I have to be able to vary the support as I go along the structure. I can't have a steady rest that just sits in the way because it won't allow me to cut the full diameter of the rod. If I use a follower rest, which actually mounts to the gantry, then I have the ability to actually vary it as I go. And that gives you a lot of extra power. that you couldn't do without it. And then lastly, if I'm cutting certain things, like if I'm cutting lead screws, I typically use a tailstock, because what that means is you've got another piece on the end with a bearing on it and a point. And so I would have a little hole on one end of the material over here. The other side would be in the chuck or in a lathe dog, and it would allow me to turn the piece, and I could move along it. So if I didn't care about the finish on the very end, but I was doing something like a lead screw, I would probably use a tailstock because it's pretty easy to do. And lastly, the spindle speed sensor and control. On a lathe, I think it's a lot more important than on a mill, because as I'm actually carving the piece, if my lathe is bogging down, I want to be able to pick the speed back up. And it's a good way of monitoring that and alternating the speed to bring it back up. But that is also critical for threading. You can't thread unless you have that. So it becomes an absolute critical piece if you want to get there. All right, so laser cutting and engraving. I've got a video at the top. You can see I'm cutting out a fan for the vacuum pump from a vacuum chuck setup. It gives you an idea of exactly how it cuts. The flashes that you see are the laser hitting the honeycomb that lies under it. It lets you know what's going on. The flashes give you a sense of assurance that the laser is actually cutting through the material, I should say. But it's pretty interesting. So what you can do, you can create two-dimensional objects, a bit like two-dimensional on the mill or two-dimensional on a 3D printer. I can cut out areas. I can etch other areas. And the examples on here probably speak to it all. At the top, you can see a face for a Thomas the Train that I cut out for my 2-year-old. I use the laser to do that. I cut the numbers and the face out. Now, those are all different pieces. I just put them together for the picture. But basically, I cut through the entire thing so that you could see it. At the very bottom, that's a granite tile tombstone that I made for a deceased pet, and that's all engraving. So the laser doesn't have the power to actually go through the granite, but it has enough to tear the edge, the outer material off, and then that allows you to visually see it. And the face, you can see there, is actually a gradient of the grayscale, so it can control the power in a very, very finite fashion. And so you can get very good detail there. It takes a lot of post-processing, but it works out beautifully. And then on the right, you can see a little blue flame. This one, the outside's cut. The edge that's frosted is actually etched. And so you can get a good picture of what you can do with acrylic. At the top, I used veneer plywood or birch Luan plywood. There, I used 3/16 acrylic. And the other one, that was a $6 tile from Home Depot. All right, so how does it work? Basically, you've got the power that you have to choose. They come in a variety of fashions, all the way up to, most of the normal ones run up to about 100 watts. As you get up in speed, it gets a lot more expensive, a lot more difficult to deal with. Mine is a 25 watt. I think SkyDog's is a 40 watt laser. For the most part, mine is very good with acrylic, and it can carve acrylic like there's no tomorrow. I can also etch glass and some of the things that you saw. Cutting wood is a pain. It's difficult. I often can't go all the way through, and I shy away from it whenever possible because 25 watts is not nearly enough to go through wood. But I make do. So there are workarounds you can do. I'm sure SkyDogs can carve wood like there's no tomorrow. As you get up to 100 watts, you can get to a lot thicker materials that you can play with and deal with. But the size typically also increases. The laser that you need to do 100 watts, I think, is 7 feet long. And so you wind up having this tube sticking out the side of it to be able to use. Speed, you control the speed just like you do on a mill or a CNC. Depending on how deep you want to cut and a lot of other things, it'll vary how quickly it moves across it. It does most of this for you. But it can cut extremely fast depending on what you're looking to do. Then the speed also varies a bit whether you're doing something called raster or vector. If you've got vector cuts that you've done in things like Inkscape and all that, it'll do a very clean job with it. If you've got raster, it's going to literally go like I don't know how many people know, but like an old dot matrix printer where you're just going row by row and you're watching it materialize. That's a bit like how it runs. And then pulses per inch. The laser actually works by like pulse width modulation. So you're actually pulsing it. And you can typically control the number of pulses that you do to control how well you deal with a material. Some materials like wood, I want a lot more pulses per inch. Some things like acrylic, I want less because I want to minimize the burn. And you can typically control it. And then lenses, you can go with a variety of different ones. Some of them are very focused, so you can do very fine detail, but they typically tend to be much more expensive. You can also, but if I were to etch, say, Super Mario Brothers in the top of my laptop, on the lid of my laptop, I would probably want a 1.0 lens. If I were to, normally I use a 2mm lens. That's the one that I have. And then some people use 4s if you just want to do large materials. And on here you can see the laser cutter at the top. I was cutting something there too. You can see that's a open logic sniffer, a case for it right there. And then you can see some of the creative ways that you build cases using a laser cutter. At the bottom is for a, I think it's from a Bus Pirate, or it might be for my, actually it's for an ISP flasher. 18 mega flasher. And you can see that I've cut 4 layers out, and the layers are successively assembled to form a case. So some of the options, if you go to a typical engraving shop, they'll have a rotary table on theirs. That's for them to do wine glasses and things like that. So it can actually carve something on the outside of a glass. Forced exhaust, I'm using a shop vac right there and just kind of blowing it out the garage. I think SkyDog does something similar with a shop vac. I just got a good exhaust blower that does 800 CFM, so I'm going to try that and see if that pushes it a little bit better. But that's critical because some of the fumes, like acrylic, reek, and they're poisonous and they reek like crazy. Another option is air assist. So typically there's a compressor that blows down right where the laser's cutting, and that's important for 2 reasons. Number one, you're always battling heat when it comes to the laser. So the longer I stay in a given spot, the more I melt, the more I burn, the more I char, the more it just ruins the work. So by using air assist, I'm actually cooling the area very quickly and trying to keep a reasonable temperature there, but it's also blowing away fragments. So as I cut the wood or the plastic, the little carbon that's left, you're blowing that out of the way so it can get a cleaner cut. And then cooling, when you look at buying a laser, if you look at some of the Chinese lasers that you can buy off of eBay, they require water cooling, so you'll actually have a pump. A lot of people just pump water out of a bucket through it because it helps keep it cool. Some people do different technologies. You could also use a chiller if you wanted to be more creative. The Versalaser and Epilog and some of those tend to be air-cooled. They're a little more convenient, but they tend to be a lot more expensive because of the type of laser that's being used. I think typically the water-cooled ones are glass and the air-cooled ones are RF. But if you're looking to get involved in it, a water-cooled one is a great way to go because you can get in at a pretty decent price. All right, so one thing I want to talk about briefly, and I'm already at 43 minutes, is the software stack that's used. So there you can see a picture of Mach 3 that I typically use. But like I mentioned in the beginning, if you don't do something with if you don't have the software to make it work, all the CNC machines in the world are going to sit idle in your garage. You have to find a way to make them function. So there are different types of software that run in stages. So there's computer-aided drafting, so I'm going to actually draw the object and model it. There's computer-aided manufacturing. That's where I'm going to tell it, okay, this line that you see here, I actually want to use a 1/8 end mill to cut this line, and I want it to go so deep. It's actually what translates it from here's a design to here's what I actually want the machine to do. And then the controller is typically the one that's sending the G-codes to the machine, or it's actually sending the steps and motion to the machine. It's what controls the overall function. And I say firmware sometimes. If you look at some of the newer, if you look at the older ways that these were done, typically it's done over a parallel port, and I'm sending actually pulses to the driver to actually make it move. On newer ones, they're trying to get to where, we're getting rid of parallel ports. So we're trying to get to where you use USB, and a lot of times there's a piece of firmware. So I'll send the G-code over a serial interface via USB, and then the firmware will interpret it into linear and circular motions so that it can be controlled. And so for a mill and lathe, this is kind of the software stack that is typically used. If I'm going to go commercial, I'm going to use SolidWorks typically. It's very good at modeling complex things. It can do lots more than I would ever dream of using it for. Visual Mill is a CAM package that supports 5th axis machining, 4th and 5th. It's very, very, very powerful, but it's also very, very, very complex. And then Mach 3 is a convenient tool, controller tool to use. It's got a lot of wizards that make things simple. And I typically use it. If you want to go the open source route, There's HeeksCAD, there's HeeksCam. Both of those are used very heavily. They're cheap, they're free, you can get them. EMC2 is free as well. You run it on RT Linux and it works like a champ. For my original V90, I actually used EMC2, and for the PCBs that you saw, I actually used EMC2, and it worked like a champ. There are no issues there, but Mach 3 makes it a little more convenient to use. For the laser cutter, I like to use SolidWorks as well for the CAD. The reason for that is because I'm typically building complex objects. They're rarely just 2D, and I want very strong dimensional capabilities, and I use SolidWorks for the other designs, so it just kind of flows that I would use it for this too. The CAM, I will output a DXF from SolidWorks and import it into Corel. Corel is kind of a de facto for doing laser work on the epilogues and the Versa lasers. And so what I do is I choose, I have hairline curves, I assign the curves a color. The printer driver actually interprets the color and chooses basically the speed and everything to run based on the color. And then the controller is device specific. The Versa laser shows up as a printer driver. I'm not sure how some of the others show up. I've had limited exposure to those. In open source, you can use HeeksCAD. You can use Inkscape for doing the vector work. I will warn you about Inkscape. Dan from our local Hackerspace does a lot of stuff in Inkscape. He sends it to me in Corel, and it is I constantly get crap that I have to deal with because it blows parts all over the place. So now what it tends to be is Dan will open it up in Inkscape or design it in Inkscape, open it up in Adobe Illustrator, save it out, and then send it to me, and then it works fine in Corel. Corel is not my favorite tool, but it is hard to beat for this. And then for a 3D printer, the commercial route is SolidWorks, NetFab, and then the controllers are mostly just open source. SolidWorks works extremely well, and like I said, I use it for everything else. For CAM, I don't use NetFab. It's very expensive. It's like $1,000, and I just haven't played with it. I haven't bothered with it. For open source, OpenSCAD is the de facto choice. Almost everybody uses OpenSCAD. If you look at Prusa or any of those guys, they actually design all their parts in OpenSCAD, but it's a language. It is a geometry language for CAD. So you're going to be, punching code in. It's a pain in the butt to deal with, but it works. SceneForge is the slicer of choice. It's written in Python. It's not fast. Some things take minutes or hours to scheme, but it's very complex software. Basically, it tells it, it carves it into layers and decides what to do. And then Pronterface is just a host controller. It's going to actually read the G code and send those over the serial port to the device. That's done by a guy named Clement, and it works very well. And I put this in here. This is kind of weird. This is, in order to get material in, one thing that you can do is you can use a CAD program to design it all. But another way is to actually use a laser scanner to do it. This isn't mature yet. It's still a work in progress. But what it basically does is it uses an interpretation of the difference in the line laser to know where the object pieces are. It does very good with white objects, and often I'll paint objects white before I try to do it. But I'm actually using an old telescope tripod with a Meade controller, and I mounted the laser line to it and running it up and down, and it works like a champ. And I'm using an old webcam that I had before. More expensive setups, they do crazy stuff. You can also, some people are trying to use Connects, but basically this is a way to get another image into the CAD program. All right, so one example that you saw in the previous one is this is the process that I went through to build the Acme nuts. So you can see here at the top, I've actually modeled the nut. What I did for my Prusa is that the ends are designed for 5mm nuts, but I wanted to use the stock 8mm nuts. I wanted to use the stock end, 8 or 5. I'm losing track now. I think it's 8. I wanted to use a stock end, but I wanted to be able to use an Acme rod that was SAE because it was convenient. And so I actually am using a metric outer diameter, but an SAE inside diameter to make it easy. And so what I did was I modeled the nut inside of SolidWorks. Then I went down to VisualCam. On VisualCam, you can actually see that there are 2 lines. The inner line is actually where I want to bore, and so I used an end mill to actually bore that hole. The outer line is just the hexagonal outside of the nut. And so you specify both. This example required 3 machining operations, and this comprises 2 of them. So here at the bottom, you can actually, or on the right, you can actually see the nut being milled. That's the outside. It's actually running as you look. At the top, this is the third machining operation. A lot of times there are these wizards built into like Mach 3 that are very, very simple to use. They're, you know, for thread milling, literally I designed all the other parts that I needed to, and then I punched what I wanted to do into Mach 3, and it did the rest for me with the thread mill. So it made it very easy. I didn't have to design it, and designing something like threads is not easy in any of the modeling tools, or not typically easy. But you can see there, I mean, I specified the diameter, the turns per inch, all that, and then it cut, and it works. You can actually see it outside in the expo area. So quickly moving on to electronics. There you can actually see a ham radio signal being pumped over my spectrum analyzer. So it's pretty cool to look at. So just a few things. At the top right, before the video stops, that's a EL wire costume for my son that I built. It actually is remote controlled, uses EL wire, has 2 different modes. It's kind of cool because it had AC and DC voltage, and it used remotes and lots of cool technologies to make him look like Tron. He's not in the costume, obviously. And then at the bottom, I'll speak about that in a minute. Some of the basics. If you want to get started doing electronics, you need a multimeter and a soldering iron. Those are the bare basics. The hand tools, you want a good pair of diagonal cutters. You want a 5 minutes, okay. All right, so you want a few things there. Just the basics. And then with an oscilloscope, it makes it very easy to look at waveforms. So you have to be careful as you look at it. It's very powerful, but it can be complex to use and can be difficult to set up. For analog circuits, it's necessary. For digital circuits, there are some easier options. And one of the options you see at the bottom is actually from a logic analyzer. So that's actually a graph from a Miss Pac-Man machine. We bought a Miss Pac-Man machine for $40. The Hackerspace did off of eBay. And I used a logic analyzer to trace down what chip was dead. So I could actually plug it into all of the different outputs, or not all, but all per chip, and actually see where the chip wasn't communicating appropriately. And basically, the pixel chip wasn't sending the displays to the screen. So we bought it for $40, and we put a $4 chip in it, and it worked fine. But that's an example of what you can do with the logic analyzer. Here's the stack here. At the top, you can see a frequency counter. If you're doing any kind of measurements, building circuits that depend upon frequency, like Doppler radios and things like that, for ham radio stuff, it's critical. You have to have one. There's almost no way around it, but there are cheap options that you can buy online and build. A spectrum analyzer is fun if you're building wireless type stuff. I would urge most of the folks in here that you probably don't need it unless you're really going to get exotic with it. A lot of times you're just going to use 2.4 gigahertz or Bluetooth or the standard bandwidths, in which case you can buy a $100 device from ThinkGeek that works just as well. A signal generator is great if I want to emulate a signal that I'm going to be passing in. It can emulate functions and signals so I can test that a circuit's behaving the appropriate way. Frequency standards typically either use a GPS or a rubidium oscillator. At the bottom right is a rubidium oscillator that I built. It actually counts the electrons running around. I didn't build the atomic part, but it counts the electrons running around the atom, and so you can actually measure. It outputs a 10 megahertz signal that is extremely accurate, down to 10 to the negative, I think, 19th or 16th. And then you can use a GPS one, which actually uses a GPS frequency, and you can synchronize it to 10 to the negative 19th. But the reason why you get this is because all of your other devices that you use are based off of a standard. And if you don't have them all calibrated properly for things like Doppler radios and everything else, you're going to be off. And even if you're a little off, they don't work properly. And so the calibration, you can only create things as well as you can measure. When it comes to milling, when it comes to lathing, if I can't measure accurately, I can't do it. And so those are some of the ones that I would have. Some of the supporting tools, I'll briefly go through this. Bench grinders help for making lathe bits. They're kind of hard to get around. Drill presses are great. Sometimes it's just too much to input something into the CAD. A metal saw, if you're going to be carving metal on a lathe or a mill, get one. They're relatively cheap, and you don't want to be cutting a piece of steel with a hacksaw, not in any quantity. And then a kiln. I actually picked up a cheap kiln off of eBay that I use to harden bits, so I can get A1 tool steel from McMaster or any one of those places, carve it on my grinder or in any of the other pieces, put in a piece of stainless foil, stick it in my kiln, and then harden it appropriately. That's a jewelry kiln. I think I paid $100 for it off of eBay. so you can find lots of things to get by. Some examples of the things I've done. There you can see a train I created for my 2.5-year-old for this Halloween. It was a lot of fun. I'll talk about that in a minute. Here you can see a quadcopter that I built. I've taken it to the show. You can see my first design at the top left, the next iteration, second gen there, the third generation at the bottom left, which is what you actually see flying. And I'm testing out the yaw and the case for the fourth generation. You can actually see it flying pretty well in my backyard. And right now I'm flying it manually, but it is a UAV quadcopter, which eventually will be fully autonomous. So it's pretty cool. Here's Thomas the Tank Engine that I built. At the top left, you can see I built an aluminum frame. Very simple. Cut the aluminum rods on my metal saw. Used a drill press to go straight through the pieces. Mounted it up to that four-wheeler that I picked up off of a curb for free. Used a friend's ShopBot, which is a 4x8 CNC, to actually carve the sides of the train, because doing it by hand would be pretty difficult. Used the standard Lowe's bucket. Actually, between the two, I actually made 3D printed parts that would secure the body to the frame, so that I had good brackets and I wasn't just using, I wasn't just doing basic stuff. It worked out really well. You can see at the bottom the bucket's mounted in. There's the train assembled. On the bottom right, you can see the laser cut pieces that I spoke about, and then you can see Thomas the Train in the middle as it's fully assembled. The other one is just the Prusa 2. At the top left are aluminum idlers that I made. Those are made on the lathe using a parting bit. They make the quality. It's a significant increase in quality to put those on the Prusa. At the top right, you can see a laser cut case that I designed and made for the electronics, basically a backpack so it would be all self-contained. At the bottom left, you can see the Acme nut that was created. And at the bottom right, you can see the ends that I turned down. And in the middle, you've got not the finished product, but where it stands today. And any of you who were here yesterday can see that I had it out on the floor. So I'm pretty much out of time. I am standing out there in the expo, so if you have questions, I don't know if we have any time for questions right now, probably not. If you have questions about any of this, please come see me. Like I said, this is my personal journey. Nobody taught me, nobody showed me how to do this. I've learned it, I've bought the stuff, and I've kind of hammered my way through it. So it may not be great, but it works. And if you've got projects, you can typically be pretty successful figuring it out. So.